All right, hello. We're going to work through the spring 2004 Exam 3 physics questions. These are the open response problems. If you haven't already done so, please attempt these, and then you can watch this video to see the solution. So let's jump in. Question 1. An electron is moving as shown, so the velocity vector is pointed to the right. And it says 1.0 times 10 to the 7 I hat meters per second. I hat goes with the x-axis. What is the magnetic field at the position of the dot? So the dot is located here. Give your answer as the components of a vector in femtotesla. Use a right-handed coordinate system. In other words, the z-axis points out of the page. Right? Okay, so let's first just write down our equation. So this comes from the Biot-Savart law. And the magnitude of the magnetic field is mu naught over 4 pi qv sine theta over r squared. All right, so this is just the equation that we use. Right? Remember, the sine theta is because of the cross product between the velocity vector and the unit vector in the r direction. All right, so let's go ahead and just kind of identify the different pieces. We've got Q, which is an electron, so this is the charge of an electron. V is given to us in the problem statement. All right, mu naught and 4 and pi are all constants. So we need theta and r. All right, so let's go ahead and take a look at those. R is the distance from the electron to the dot. All right, so let's kind of highlight that. So this is r right there. We need to simply use Pythagorean's theorem to find out what that is. So we can go down and across. So this is 4 centimeters down and then 4 centimeters across. All right, and so then we can calculate what r is using Pythagorean's theorem. So this is going to be 4 squared plus 4 squared and the square root of that. So this is the square root of 32 centimeters. All right, and so we can use that in our equation. We'll need to convert it to meters in order to get all the units to work out. Okay, the theta is this angle right here. So it's the angle between the velocity vector and the r, the unit vector in the r direction. And so this is also the same as this angle here. There's different ways that we can figure this out, but that angle comes out to be 45 degrees. So then we can just plug everything in to calculate the magnitude. And then instead of Q, I'll put E. And then for V, I'm going to put 10 to the 7 meters per second sine of 45 over r squared. So r is 32 centimeters, so r squared is, root 32. So it's 32 centimeters squared. And so that comes out to be 32 times 10 to the minus 4 meters squared when you square it. All right, and we can calculate this, noting that both mu and e are constants that are in our calculator. When I crunched the numbers, I got 4.26 times 10 to the minus 17 Tesla. And then it asks for us to give it in components in femtotesla. So this is just the magnitude. So in order to convert this to femtotesla, we have to multiply by 10 to the 15 femtotesla per Tesla. And so this is going to be 0.0426 femtotesla. Now this is the magnitude. We got to break this into its components. So let's apply the right-hand rule of this, figure out what the direction is. And according to the right-hand rule, we want V cross R. So V is pointing in this direction, cross R. So if we apply our right hand rule, it would be pointing into the board or into the page, okay? But this is an electron, right? And so because it's an electron, we have to reverse the direction. So B points out of the page because it's an electron, all right? So then we can rewrite B in terms of components. That's all of B is in the Z direction. So it's 0.0426 k hat femtotesla. All right, so we can write that in component form, and that would be our answer. All right. Okay, so next problem. A proton is moving in a magnetic field of B equals 0.2 I hat Tesla. So the B field is pointing to the right. All right, let me just illustrate that with it's a little hard to see. So I will illustrate it with some blue. All right, with a speed of 1 times 10 to the 6 meters per second in the directions shown, what is the magnetic force on the proton? Give your answer as components of the force in piconewtons. All right, so in order to solve this problem, we need to notice that the velocity vector is pointing like this, and this angle is 45 degrees. All right. So this is pointed at a 45-degree angle below the x-axis. All right. So this is 45 degrees between the x and the negative z-axis. Axes. All right. So the magnitude of the force is simple to calculate. It is QVB sine theta, all right, where theta is the angle between the velocity vector and the B field vector, which in this case is 45 degrees. It is labeled in the problem statement. So the force that's acting on the proton is the charge of the proton, which is the elementary charge, the speed of the proton, which is 10 to the 6 meters per second, the magnitude of the magnetic field, which is 0.2 Tesla, and then the sine of the angle, sine of 45. So if we crunch all those numbers, I got 2.73 times 10 to the minus 14 newtons. We're asked to give as components of the force in piconewtons. So I need to multiply this by 10 to the 12 piconewtons per newton. So when I do that, I get 0.0273 piconewtons. So I need to break this into its components. All right, so I need to apply the right-hand rule to this. And according to the right-hand rule, we need V cross B. All right, so V cross B, V is pointing diagonally down in the XZ plane, and B is pointing along the x-axis. All right, so when we do V cross B, so we point our fingers in the direction of V, we wrap them in the direction of B, so it's like this. V, I can't move my hand that far, but V cross B, my thumb is pointing up, so the thumb is pointing up, so that's out of the page, which is along the negative y-axis, okay? So because it's in the negative y direction, all of the magnitude is aligned with the j hat. So I can write this in component form as negative 0.273 j hat piconewtons, and then that'll be my final answer for that one. All right, number 3. There we go. So the loop is being pushed into a 0.2 Tesla magnetic field at 100 meters per second, so the velocity vector is up. The resistance of the loop is 1 ohm. What is the magnitude and direction of the current in the loop? We actually have 2 ways that we can solve this. One is by looking at the changing magnetic flux inside the loop using Faraday's law and then Lenz's law to figure out the direction. The other is by using the movement of a wire in a magnetic field. All right, so there's wires that are oriented in this direction and then a wire that's oriented in this direction. All right, and we can sort of add all of those up to find out what the potential is. And because these 2 segments of wire are aligned with the velocity vector, then there is no current moving through the wire caused by those segments. All of the potential is caused by the segment that is perpendicular to the motion. So if we want to just use that, we can say this is the potential for a wire is VLB, noting that this wire is perpendicular to the velocity vector. So when we do the cross product, the sign is 1, so I don't need to worry about the sign. And then this is going to equal, using Ohm's law, I times R. So we can just solve for I, which is VLB over R. Now if this wire was at an angle, I would have to include the sign of the angle between the segment of that wire and the velocity vector. Okay, so this is going to equal, we can just plug everything in. The velocity is 100 meters per second. L is 5 centimeters. Which is 0.05 meters. The B field is 0.2 Tesla, and the resistance is 1 ohm. So when I crunch all of this, I get 1 amp for the current. Now, in order to find the direction, I have to apply the right-hand rule, okay? And the right-hand rule that we're wanting to apply is either looking at the right-hand rule of this line segment or applying the right-hand rule for Lenz's law and doing it that way. So either way is appropriate. We want V cross B, and this is going to be give you the direction of the force, okay? And so if we do this, we'll see the direction of the force on the positive charge carriers in this line segment. So I'll go V cross B, which is the velocity, the B field is up. So the force is to the right in this top segment here. So we got force to the right. So that's the force on the positive charge carriers. So I is going to be in this direction. So I is, and that is a clockwise direction from the vantage point that we are looking. All right. Okay, here we go. The 300 microfarad capacitor in the figure is initially charged to 100 volts. The 1200 microfarad capacitor is uncharged, and the switches are both open. what is the maximum voltage to which you can charge the 1200 microfarad capacitor by the proper opening and closing of the two switches? A, describe how the switches should be open and closed. B, the answer to this problem is this. Show how this answer is obtained, starting with one or more of the equations. All right, I'm going to show you two ways to solve this. They both give you the same answer. But let's first describe how the switches should be open and closed. So part A, everything is here. Essentially what we're going to do is transfer the energy from the capacitor to the inductor. And then we want to transfer the energy from the inductor to this capacitor. All right, so for part A, in order to transfer the energy to the inductor, we're going to close switch S1 until the capacitor's voltage is 0 and the current in the inductor is at a maximum. Until delta V of the capacitor equals 0 and I inductor is at a maximum. Okay? All right, and then we will open S1 and close S2. All right, so this is a maximum current. We essentially want to take all of that energy and then transfer it over here. So we open this switch to disconnect this capacitor, close this switch to connect this capacitor. And until delta VC is at a maximum and IL equals 0. All right, so this is going to transfer all of the energy to this 1200 microfarad capacitor, and then open S2. All right, so that's the timing of what we want to do. So we're going to close this, transfer energy here, open, close, transfer energy here. All right, so here's the answer. Let's just figure out how we can solve this. So let me show you two different ways that you can solve it. We'll start with using the charge equation on the capacitor. Q is Q naught cosine omega t. All right. So so this is just the charge on the capacitor that you start with. All right. And if I want to figure out what the maximum current is, I got to take the derivative of this. So I is dq dt, and this is going to be equal to negative omega q naught, sine of omega t. Okay, so notice that these are time varying currents and charges that are in the capacitor. So in order to get the maximum of this, the maximum current is going to be when the sine function is, in this case, -1. So I'm just looking for the maximum. So I max is equal to omega q naught, what the starting charge is in the capacitor. All right. So this is going to be the same no matter which side we're going to. Either q naught, is here or over here. So we're just transferring the charge from one to the other. But we're given voltage, so we need to convert this into voltage. The voltage is related to the capacitor. Q naught is equal to delta V naught times C, the capacitance. All right. So I can look at this for the left-hand side and the right-hand side and essentially set up an equation. That is, the starting charge on the left-hand side, which is delta V naught C. So we'll call this, so we're plugging this in here. All right, so we have omega 1 V1 C1 equals I max. Okay, so this is the first one over here. We plug this in here. And then this is going to equal omega 2 V2 C2. All right, so this relates the voltage on the first capacitor with the voltage on the second capacitor. All right, so we're just using this equality to get here. And then omega for these kinds of problems is the square root of 1 over LC. So omega is the square root of 1 over LC. So omega 1 is the square root of 1 over LC1. And then omega 2 is the square root of 1 over LC2. And then all we need to do is solve for V2, which is the 1200 volt voltage, and L's cancel on both sides. Half of this cancels with half of that, and half of that cancels with half of that. So you wind up with V1 square root of C1 equals V2 square root of C2. And then I can just solve for this to arrive at that equation. All right, so that's one way to do it. Let me show you one more way, and that is the energetic analysis. This is a little bit easier conceptually because we're just transferring energy from here to here. So we have the energy in the first capacitor is equal to 1/2 V1 squared C1. This is just the energy that's in a capacitor. And then we're going to transfer that to the inductor, which is 1/2 L I squared. So we're moving the energy here. Then we're going to move the energy, oops, that's C2, sorry. Then we're going to move the energy here. So we're moving the energy to the inductor and then to the other capacitor. In other words, we're doing this right here. So we can set those two equal to each other because the energy in the first capacitor is going to equal the energy in the second capacitor. So I would have 1/2 V1 squared C1 equals 1/2 V2 squared C2. And my 1/2s cancel, and I can arrive at the same kind of equation by taking the square root. All right, that's it.